So here's something worth thinking about as you settle in tonight. Right now, somewhere on this planet, there are roughly 13,000 nuclear warheads. Some of them are sitting in silos beneath wheat fields in Montana and Wyoming. Some are tucked inside submarines, drifting silently under the North Atlantic. A few are stored in bunkers in the Belgian countryside, which is a strange thought if you've ever been to Belgium. And every single one of those weapons traces back to a series of discoveries that started, really, with people who had no idea what they were about to unleash. Scientists who were just trying to understand what matter was made of. That's where we're going tonight, all the way back to the beginning, and then slowly, gently forward through the whole strange story of how humans figured out how to split atoms and then, almost immediately, turned that knowledge into the most destructive force ever created. And along the way, I want to untangle all the confusing parts, the physics that seems impenetrable but actually isn't, the difference between fission and fusion, how a bomb actually works, mechanically, step by step, why some materials are weapons grade and others aren't. All of it. We'll take it slow. There's no rush. If you drift off somewhere in the middle, that's perfectly fine. That's kind of the point. Let's start with atoms, because everything starts with atoms. For most of human history, people had no idea atoms existed. The ancient Greeks had a philosophical concept. Democritus, around 400 BC, argued that if you kept cutting matter into smaller and smaller pieces, eventually you'd reach something indivisible, something he called atomos. But that was just a thought experiment. Nobody could prove it. And for over 2,000 years, that's basically where things stayed. Atoms were an idea, not a fact. Then the 1800s happened, and chemistry started getting serious. John Dalton proposed his atomic theory in 1803, suggesting that each chemical element was made of identical tiny particles. That was a big step. But even Dalton's atoms were imagined as little solid balls, like miniature billiard balls, perfectly round, perfectly simple. Nobody knew what was inside them, because as far as anyone could tell, there was no inside. Atoms were the smallest thing. End of story. Except it wasn't the end of the story. Not even close. The first crack in that idea came in 1897 in a laboratory at Cambridge University, when a physicist named J.J. Thomson discovered the electron. He was experimenting with cathode rays. Basically, he was shooting electrical current through a vacuum tube and watching what happened. And what he found was that the rays were made of tiny particles much smaller than any atom. Particles with a negative electrical charge, which meant atoms couldn't be solid little balls after all. There was something inside them, something smaller. Thomson proposed what became known as the plum pudding model. Imagine a blob of positive charge, like the pudding, with little negative electrons embedded in it, like raisins. It sounds quaint now, but it was revolutionary at the time. For the first time, scientists were saying that atoms had internal structure. They were made of parts. And here's the thing about discovering that something has parts. Once you know there are parts, you immediately want to know how they're arranged. What's the architecture? What holds it all together? And that question, that simple, curious question, is what eventually leads to nuclear weapons. Not directly, not overnight, but it's the thread. Pull on it long enough, and you end up at Hiroshima. The next big leap came from one of Thomson's own students, a New Zealander named Ernest Rutherford. Rutherford was one of those larger-than-life figures in physics. Big personality, booming voice, enormous mustache. He once said that all science is either physics or stamp collecting, which gives you a sense of his confidence. In 1909, working at the University of Manchester, Rutherford and his colleagues Hans Geiger and Ernest Marsden conducted one of the most famous experiments in the history of science. They fired tiny alpha particles, which are basically little chunks of helium nuclei, at an incredibly thin sheet of gold foil, and they watched where the particles went. Now, if Thomson's plum pudding model was right, most of those particles should have passed straight through the foil with maybe a slight deflection, because the positive charge in each atom would be spread out evenly, like a diffuse cloud. And most of the particles did pass straight through, but some of them bounced back. Not just deflected, bounced back, almost straight back toward the source. Rutherford later said it was as if you fired a cannon shell at a piece of tissue paper and it came back and hit you. Think about what that means. Something inside those gold atoms was dense enough and concentrated enough to send an alpha particle flying backward. And from the angles and the statistics of those deflections, Rutherford worked out that almost all the mass of an atom was concentrated in an incredibly tiny, incredibly dense core. He called it the nucleus. The atom, it turned out, was mostly empty space. If you blew up an atom to the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line, and the electrons would be like gnats buzzing around somewhere up in the nosebleed seats. Everything else, all that space between, is nothing. Just emptiness. That's a wild thing to realize. The chair you're lying on right now, the walls of your room, your own body, it's almost entirely empty space. The reason things feel solid is because of the electromagnetic forces between electrons, not because matter is actually packed tight. But that nucleus, tiny as it is, contains almost all the mass. And that means the energy holding it together is enormous. We'll come back to that energy. That's the whole game, really. But let's stay with the history for a moment, because the next couple of decades are when things start moving fast. By the early 1930s, physicists had figured out that the nucleus itself was made of two kinds of particles: protons, which carry a positive charge, and neutrons, which carry no charge at all. The proton had been identified by Rutherford back in 1917 or so, but the neutron wasn't discovered until 1932 by James Chadwick, also working at Cambridge. And the neutron turned out to be incredibly important, not just for understanding atomic structure, but specifically for what comes later with nuclear weapons. The neutron is the key that unlocks everything. And here's why. Protons are positively charged, right? And the nucleus is full of protons packed incredibly close together. Now, you know from everyday experience that like charges repel each other. If you've ever tried to push two magnets together the wrong way, you've felt that resistance. So how do all those protons stay crammed together in the nucleus without flying apart? There must be some force holding them in, some force stronger than the electromagnetic repulsion trying to push them apart. And there is. Physicists call it the strong nuclear force. It's the strongest force in nature, but it only operates over incredibly tiny distances, basically the scale of the nucleus itself. Step even slightly outside that range and it drops to zero. It's like the world's strongest glue, but it only works if things are already touching. So the nucleus is this delicate balance. The strong force is pulling everything together, and the electromagnetic force is trying to push the protons apart. For small atoms, hydrogen, helium, carbon, oxygen, the strong force wins easily. The nucleus is stable. It just sits there, perfectly happy, for billions of years. But as atoms get bigger, As you add more and more protons, that balance gets harder to maintain. The electromagnetic repulsion grows because every proton repels every other proton across the whole nucleus. But the strong force only acts between immediate neighbors. It's like trying to hold a crowd together with short pieces of rope. Works fine for a small group, but once the crowd gets big enough, the people on the edges start drifting away. This is why the heaviest natural elements, things like uranium and thorium, are radioactive. Their nuclei are so large, so packed with protons, that they're barely holding together. They're right on the edge of stability. And sometimes, spontaneously, a nucleus will shed a piece of itself, an alpha particle, a beta particle, trying to reach a more stable configuration. That's radioactivity. It's not some mysterious energy from nowhere. It's an overstuffed nucleus trying to find a more comfortable arrangement. Now, uranium. Let's talk about uranium, because this is where the story really starts to narrow toward weapons. Uranium is element 92 on the periodic table. 92 protons in its nucleus, which makes it the heaviest element that occurs naturally in any significant quantity on Earth. It was discovered in 1789 by a German chemist named Martin Klaproth, who named it after the planet Uranus, which had been discovered just 8 years earlier. For over a century, uranium was mostly a curiosity. It was used to color glass and ceramics, a nice yellowish green. Nobody thought it was particularly important. That changed in 1896, when a French physicist named Henri Becquerel accidentally discovered radioactivity. He'd been experimenting with uranium salts and photographic plates, and he found that the uranium was emitting some kind of invisible radiation all on its own, without any external energy source. Marie and Pierre Curie followed up on Becquerel's work and discovered even more intensely radioactive elements, polonium and radium. Marie Curie coined the term radioactivity. She won 2 Nobel Prizes for her work. She also, tragically, died of aplastic anemia almost certainly caused by years of radiation exposure at a time when nobody understood how dangerous it was. Her laboratory notebooks are still so radioactive that they're kept in lead-lined boxes, and you have to sign a liability waiver to look at them. But here's what matters for our story. Radioactivity showed that atoms weren't permanent. They could change. They could break down, transform, release energy, and the amount of energy involved was staggering compared to anything in chemistry. When you burn coal, you're rearranging electrons between atoms, chemical energy. But radioactive decay involves changes to the nucleus itself, and because of that delicate balance we talked about, the energies are millions of times larger. Einstein had published his famous equation, E equals mc squared, in 1905, showing that mass and energy are interchangeable. A tiny amount of mass, converted to energy, produces an enormous amount. And nuclear reactions, it turned out, did exactly that. They converted a tiny bit of mass into a tremendous amount of energy. So by the early 1930s, all the pieces were on the table. Scientists knew about protons and neutrons. They knew about the strong force and electromagnetic repulsion. They knew that heavy nuclei were barely stable. They knew that nuclear reactions released extraordinary amounts of energy. And they had the neutron, this uncharged particle that could approach a nucleus without being repelled because it carried no electrical charge. A proton trying to get close to a uranium nucleus would be pushed away by all those other protons. But a neutron could just drift right in, unimpeded, like someone walking through an open door. And that's exactly what a handful of physicists in Rome, Berlin, and Paris started doing in the mid-1930s. They started firing neutrons at various elements to see what would happen. Enrico Fermi, working in Rome with his team, systematically bombarded element after element with neutrons. When he got to uranium, something strange happened. He got results he couldn't quite explain. He thought he might have created new elements heavier than uranium, elements that didn't exist in nature. The scientific community was excited but confused. It took 4 more years for anyone to figure out what was actually going on. And the people who finally cracked it were working in Berlin in December of 1938, at one of the most fraught moments in modern history. Otto Hahn and Fritz Strassmann, 2 German chemists, repeated the neutron bombardment experiments on uranium and carefully analyzed the products. And what they found made no sense to them at first. Instead of elements heavier than uranium, they were finding barium, element 56, an atom with barely more than half the protons of uranium. It was as if the uranium nucleus had broken roughly in half. Hahn was baffled. He wrote to his longtime collaborator, Lisa Meitner, who was by then a refugee in Sweden. She'd been forced to flee Nazi Germany because of her Jewish heritage, despite decades of brilliant work. Meitner received Hahn's letter while visiting relatives for Christmas, and it was Meitner, together with her nephew Otto Frisch, who figured out what was happening. Walking through the snowy Swedish countryside, they worked through the physics. The uranium nucleus, they realized, was so unstable, so delicately balanced between the strong force and electromagnetic repulsion that when it absorbed an extra neutron, it could become so agitated that it literally split apart. The nucleus would elongate, like a water droplet stretching, and the electromagnetic repulsion between the 2 halves would overcome the strong force, and the nucleus would tear itself in 2. 2 smaller nuclei, flying apart with tremendous energy. Frisch, who was also a biologist by hobby, borrowed a term from cell biology. When a living cell divides, it's called fission. So he called this process nuclear fission. And when Meitner calculated the energy released, using Einstein's equation, comparing the mass of the original uranium nucleus to the masses of the 2 fragments, the numbers were staggering. About 200 million electron volts from a single atom splitting. Now that number might not mean much on its own, so let's put it in perspective. A typical chemical reaction, say burning a molecule of coal, releases maybe a few electron volts of energy. That's it. A few. And here was a single uranium atom releasing 200 million. That's roughly 100 million times more energy per atom than any chemical reaction known to science. Meitner stared at those numbers in the Swedish snow, and she knew immediately that this was something the world had never seen before. And here's what made it even more extraordinary. When that uranium nucleus split, it didn't just release energy, it also released extra neutrons, 2 or 3 of them, flying off from the fission fragments. And if you think about that for a moment, you start to see the terrifying possibility that physicists around the world began to see almost immediately. Because what happens if one of those released neutrons hits another uranium nucleus? That nucleus could split too, and release more neutrons, which could hit more nuclei, which could split and release still more neutrons. Each generation multiplying, each fission event releasing that enormous burst of energy. A chain reaction. The idea wasn't entirely new. Leo Szilard, a Hungarian physicist living in London, had actually conceived of the possibility of a neutron chain reaction back in 1933, years before fission was even discovered. He'd been so worried about the implications that he'd filed a secret patent and assigned it to the British Admiralty to keep it out of public view. But in 1933, nobody knew a mechanism that could actually produce such a chain reaction. Now, in early 1939, Fission provided exactly that mechanism. The news spread through the physics community with breathtaking speed. Frisch told Niels Bohr in Copenhagen just before Bohr boarded a ship for America in January 1939. By the time Bohr arrived in New York, he was bursting with the news, and within days, physicists at Columbia University, Johns Hopkins, the Carnegie Institution, labs all over the United States were replicating the experiment. They were splitting uranium atoms on their own lab benches and confirming everything. Fission was real. The energy release was real. And the extra neutrons were real. Now, you have to understand the moment. It's February 1939. Hitler has already annexed Austria. He's taken the Sudetenland. Kristallnacht happened just weeks before Hahn and Strassmann's discovery. Europe is sliding toward war, and everyone knows it. And suddenly, physicists, many of them refugees from fascism themselves, realize that the laws of nature have just revealed a pathway to a weapon of almost inconceivable power. The mood in the physics community shifted overnight from pure intellectual excitement to something much darker. Because the question was no longer whether such a weapon was theoretically possible. The question was whether someone could actually build one. And the far more urgent question, could Germany build one first? This is where Leo Szilard comes back into the story, and he's such a fascinating character. Szilard was brilliant, restless, perpetually worried, and almost pathologically unable to sit still. He'd fled Hungary, then Germany, then he ended up in England, and eventually in America. He didn't have a permanent academic position for most of this period. He just showed up at laboratories, talked to people, had ideas, and moved on. But he was deeply, viscerally afraid of what would happen if the Nazis got an atomic bomb, and he knew that Germany had some of the best nuclear physicists in the world. Werner Heisenberg was still there. So was Carl Friedrich von Weizsäcker. Germany had access to uranium ore. They had heavy water from Norway. Szilard couldn't sleep at night thinking about it. So Szilard did something remarkable. He convinced Albert Einstein, the most famous scientist in the world, to sign a letter to President Franklin Roosevelt warning him about the possibility of atomic weapons. The letter, dated August 2nd, 1939, is one of the most consequential documents of the 20th century. Einstein's name gave it weight, but the ideas and the urgency were largely Szilard's. The letter explained, in careful but clear language, that recent research on uranium chain reactions might lead to the construction of extremely powerful bombs, and that the United States should begin its own research program immediately. It also noted, pointedly, that Germany had stopped the sale of uranium from mines in occupied Czechoslovakia, a sign that the Germans might already be pursuing the same idea. Roosevelt received the letter in October 1939, by which point World War II had already begun. He appointed an advisory committee on uranium, which initially moved with agonizing slowness. The early funding was almost comically small, a few $1,000s here and there. The bureaucracy didn't understand the physics, and the physicists didn't know how to navigate the bureaucracy. For about 2 years, the American effort was scattered, underfunded, and uncertain. There were fundamental questions that still needed answering. Could you actually sustain a chain reaction? How much uranium would you need? And which isotope of uranium was the one that would fission? That last question, which isotope, turned out to be absolutely crucial, and it's worth slowing down to explain why. Because this is one of those things about nuclear weapons that confuses a lot of people, and once you understand it, everything else makes much more sense. So uranium as you find it in nature is a mixture of isotopes. Remember, Isotopes are atoms of the same element, same number of protons, but with different numbers of neutrons. Natural uranium is overwhelmingly uranium-238, which has 92 protons and 146 neutrons. About 99.3% of all natural uranium is U-238, but mixed in, at a concentration of only about 0.7%, is uranium-235, which has 3 fewer neutrons. And here's the thing. It's U-235 that fissions easily. When a slow-moving neutron hits a U-235 nucleus, that nucleus splits readily, releasing energy and more neutrons. U-238, on the other hand, tends to just absorb the neutron without splitting. It captures it and becomes U-239, which is interesting for other reasons we'll get to later, but it doesn't give you a chain reaction. So the problem is immediately obvious. The stuff you need, U-235, makes up less than 1% of natural uranium, and separating it from U-238 is nightmarishly difficult. Why? Because isotopes of the same element are chemically identical. They have the same number of protons, the same number of electrons, the same chemical behavior. You can't separate them with any chemical process. The only difference between U-235 and U-238 is 3 neutrons, which gives U-235 a slightly lower mass. Slightly. We're talking about a mass difference of roughly 1.3%. So you have to find some physical process that can exploit that tiny mass difference to separate the two isotopes, and you have to do it on an industrial scale, processing tons and tons of uranium to extract enough U-235 for a weapon. In 1940, nobody had ever done anything remotely like that. But there was another path, and this is where the story gets even more interesting. Remember how I said U-238 absorbs a neutron and becomes U-239? Well, U-239 is unstable. It undergoes beta decay. It spits out an electron, which effectively converts one of its neutrons into a proton. So U-239 becomes element 93, Neptunium-239. And Neptunium-239 is also unstable, and it also beta decays, turning into element 94, an element that didn't exist in nature, an element that had to be created, atom by atom, in a laboratory. In 1940 and 1941, a team at the University of California, Berkeley, led by Glenn Seaborg, along with Edwin McMillan, Joseph Kennedy, and Arthur Wall, produced and identified this new element. They named it plutonium, after the planet Pluto, continuing the tradition that had given us uranium after Uranus and Neptunium after Neptune. And here's what made plutonium so important. Plutonium-239 turned out to be fissile. Like U-235, it could sustain a chain reaction, and you could produce it from U-238, which was abundant, by bombarding it with neutrons in a reactor. So now there were 2 possible paths to a bomb. You could either painstakingly separate U-235 from natural uranium, or you could manufacture plutonium in a nuclear reactor. The American program would eventually pursue both paths simultaneously, because nobody was sure which one would work, and the stakes were too high to gamble on just one. But before any of that could happen at scale, someone needed to prove that a self-sustaining chain reaction was even possible. And that brings us to Chicago, and to Enrico Fermi, who we met earlier trying to bombard uranium with neutrons in Rome. Fermi had left Italy in 1938. He'd used his Nobel Prize trip to Stockholm as an escape route, bringing his family to the United States rather than returning to Mussolini's Italy. His wife Laura was Jewish, and the racial laws that Italy had adopted made staying impossible. So Fermi ended up at Columbia University and then at the University of Chicago, where he was tasked with building the world's first nuclear reactor. They called it a pile, Chicago Pile 1, because that's essentially what it was. A carefully constructed pile of uranium and graphite blocks stacked in layers in a squash court underneath the stands of the university's abandoned football stadium. The graphite served as a moderator. It slowed down the neutrons released by fission, which made them more likely to be captured by U-235 nuclei and cause more fission. Think of it like this. A fast neutron zips right past a uranium nucleus without interacting, like a car speeding past a hitchhiker. But a slow neutron, one that's been bounced around through graphite until it's lost most of its kinetic energy, is much more likely to be absorbed. The graphite was the braking system. Fermi's team built the pile by hand, block by block, over the course of weeks in the fall of 1942. They machined roughly 45,000 graphite blocks and arranged them with uranium metal and uranium oxide distributed throughout. Control rods made of cadmium, a material that eagerly absorbs neutrons, were inserted into the pile. As long as the cadmium rods were in, they'd soak up enough neutrons to prevent a chain reaction. Pull the rods out, and if the pile was designed correctly, the reaction would go critical. Each fission event would produce, on average, at least one neutron that went on to cause another fission. Self-sustaining. On December 2nd, 1942, in that cold squash court with about 40 people watching, some of them standing on a balcony above, which, when you think about it, was an extraordinarily dangerous place to be, Fermi gave the order to withdraw the control rods, one step at a time. He watched the neutron counters. The clicking of the detectors grew faster and faster. The instruments showed the neutron flux rising steadily, exactly as Fermi's calculations predicted. At 3:25 in the afternoon, the reaction went self-sustaining. For the first time in history, humans had created a controlled, self-sustaining nuclear chain reaction. Fermi let it run for about 28 minutes, then ordered the control rods reinserted. The reaction stopped. Arthur Compton, who was overseeing the project from above, made a coded phone call to James Conant at Harvard. "The Italian navigator has landed in the New World," Compton said. Conant asked, "How are the natives?" "Very friendly," Compton replied. It was a moment of quiet triumph, but also a threshold, because what Fermi had just demonstrated wasn't just a scientific milestone, it was proof of concept. The chain reaction worked. The physics was real. And now the question was no longer whether you could harness the energy of the atom, but how fast you could turn that knowledge into a weapon. And that's exactly what happened next, at a speed and scale that, honestly, still feels hard to believe even when you know the numbers. Because here's the thing about December 1942. The chain reaction in that squash court proved the physics, but it didn't build a bomb, not even close. What Fermi's pile produced was about half a watt of power. Half a watt. That's less than a small flashlight. The pile eventually ran at about 200 watts in later experiments, which is roughly enough to power a couple of light bulbs. To build a weapon, you needed to go from a controlled trickle of fission events in a carefully stacked pile of graphite to an uncontrolled runaway explosion releasing the energy equivalent of thousands of tons of TNT, all in a fraction of a millionth of a second. And you needed enough of the right material, either uranium-235 or plutonium-239, to make it happen. Getting that material was the single hardest engineering challenge of the entire project, and arguably one of the most difficult industrial undertakings in human history. So let's talk about that. Let's talk about what it actually took. By the time Fermi's pile went critical, the Manhattan Project was already ramping up. It had been reorganized under military leadership in September 1942, just a few months earlier, when the Army Corps of Engineers established the Manhattan Engineer District. That's where the name comes from, by the way, just a bureaucratic designation based on the Corps' office in Manhattan. And the man put in charge was Colonel Leslie Groves, who was promoted to Brigadier General almost immediately. Groves is one of those figures who doesn't get romanticized the way the scientists do. But without him, it's genuinely hard to imagine the bomb being built on the timeline it was. He was a career military engineer. He'd just finished overseeing the construction of the Pentagon, the actual Pentagon building, which at the time was the largest office building in the world. He was blunt, demanding, often abrasive, and extraordinarily effective at getting enormous things built on impossible schedules. He was not a man who tolerated delay. Groves made several critical decisions almost immediately. The first was to pursue every possible path to fissile material simultaneously. This is important. A more cautious approach would have been to study each method, pick the most promising one, and focus resources there. Groves didn't do that. He couldn't afford to, because the fear, and this was very real in 1942 and 1943, was that Germany was working on its own bomb. Heisenberg, one of the greatest physicists of the 20th century, was leading the German nuclear program. Nobody on the Allied side knew exactly how far along the Germans were, and the assumption was that they might be ahead. So Groves bet on everything at once. Multiple paths to uranium-235, a separate path to plutonium, all running in parallel, all at full industrial scale, all burning through money at a rate that would have caused a political scandal if anyone outside a tiny circle had known about it. Let's start with uranium, because that's where the difficulty really hits you. Remember, natural uranium is about 99.3% U-238 and only 0.7% U-235. And it's the U-235 you need for a bomb. That's the isotope that fissions readily when hit by a slow or fast neutron. U-238 mostly just absorbs neutrons without splitting, at least under normal conditions. So you need to separate the two isotopes. And here's the nightmare. They're both uranium. They're chemically identical. Same number of electrons, same chemical behavior. You can't use any chemical process to tell them apart. The only difference is their mass. U-235 has 3 fewer neutrons than U-238, which means it's about 1.3% lighter. That's it. That's all you have to work with. A 1.3% difference in mass between two atoms of the same element. Think about what that means from an engineering standpoint. You need to process tons, literally tons, of uranium, and sort atoms that are almost exactly the same weight into two piles. It's like someone dumps 1 million ping pong balls on a table and tells you that 1% of them are very, very slightly lighter than the rest, and you need to find those ones. Except the balls are atoms. You can't touch them, and you need to do it on an industrial scale in the middle of a war. 3 main approaches were pursued. The first was gaseous diffusion. The idea here is elegant in principle and monstrous in practice. You convert uranium into a gas, uranium hexafluoride, a nasty corrosive compound, and then you push that gas through a barrier with incredibly tiny pores. Molecules containing the lighter U-235 move slightly faster than molecules containing U-238 because lighter molecules at the same temperature have higher average velocity. So when the gas hits the barrier, the lighter molecules are slightly more likely to pass through. But, and this is the key, only slightly. Each pass through a barrier enriches the uranium by a tiny, tiny fraction. To get from natural uranium at 0.7% U-235 up to weapons grade, which is about 90% U-235, you need to repeat this process thousands of times. Thousands of stages, connected in a cascade, each one feeding its slightly enriched output to the next stage. The plant built for this was called K-25, and it was constructed at Oak Ridge, Tennessee, on a site that had been farmland and small towns just months before. K-25 was, at the time, the largest building in the world under one roof. It was U-shaped, and each arm of the U was about half a mile long. The building covered 44 acres. Inside were thousands of diffusion stages, miles of piping, and those barriers. The barriers were perhaps the single most difficult manufacturing challenge of the entire project. They had to have pores small enough to exploit the tiny mass difference between U-235 and U-238 hexafluoride molecules. They had to withstand the corrosive uranium hexafluoride gas, and they had to be manufactured in enormous quantities to a standard of precision that pushed the absolute limits of 1940s materials science. Teams tried nickel mesh barriers, powdered nickel barriers, various alloys. The problems were relentless. Barriers cracked, barriers corroded, barriers clogged. The entire gaseous diffusion program nearly collapsed multiple times under the sheer difficulty of making those barriers work. The second approach was electromagnetic separation, and this one has a wonderful, almost absurd quality to it. It was championed by Ernest Lawrence at Berkeley, the same Lawrence who'd invented the cyclotron, the particle accelerator. Lawrence's idea was essentially to build a giant mass spectrometer. You ionize uranium atoms, strip off electrons so they become charged, then shoot them through a magnetic field. Charged particles curve in a magnetic field, and the radius of that curve depends on their mass. Heavier U-238 ions curve on a slightly wider path than lighter U-235 ions. So at the end of the path, the two isotopes land in slightly different spots, and you collect them in separate receivers. It's beautifully direct. You're literally sorting atoms by weight using magnets. The machines Lawrence designed for this were called calutrons, a portmanteau of California University cyclotrons. And they were built at Oak Ridge, too, in a facility called Y-12. Hundreds of these machines, arranged in giant oval racetracks, each one containing powerful electromagnets. And here's a detail that tells you something about the scale of wartime desperation. The electromagnets required enormous amounts of copper wire for their coils, but copper was a critical war material, desperately needed for shell casings and wiring and 100 other military uses. So the Manhattan Project borrowed 14,000 tons of silver from the U.S. Treasury, actual silver bullion from the vaults at West Point, and used it instead of copper. Silver is an even better electrical conductor than copper. Treasury officials were reportedly horrified, but they handed it over. After the war, every ounce was returned, melted down and accounted for. The calutrons worked, but they were painfully slow and inefficient. Each machine produced tiny amounts of enriched uranium. They were also temperamental. The ion beams were unstable, the vacuum systems leaked, the collectors got contaminated. And here's a fascinating human detail. The calutrons required constant manual adjustment by operators who watched dials and tweaked controls to keep the ion beams focused. The physicists initially ran the machines themselves and struggled. Then someone had the idea to hire young women from the local Tennessee towns, women who had no physics background, but were patient, attentive, and good at following precise instructions. These operators, many of them fresh out of high school, ended up running the calutrons more efficiently than the PhD physicists had. They didn't overthink it. They just watched the dials and made the adjustments, exactly as trained. It's one of those stories that reminds you that engineering at scale is always about people, not just principles. The third enrichment method was thermal diffusion, a simpler but less efficient approach where you run uranium hexafluoride through tall columns with a hot pipe in the center and a cool wall on the outside. The lighter isotope tends to concentrate near the hot surface and rise, while the heavier isotope drifts toward the cool wall and sinks. It produces only slightly enriched uranium, but it could serve as a first stage, feeding partially enriched material into the other processes. A thermal diffusion plant called S50 was built at Oak Ridge in a remarkable hurry, just 69 days from groundbreaking to operation. Now, here's where Groves's parallel approach paid off. None of these methods alone could produce enough weapons-grade uranium fast enough. But chained together, thermal diffusion feeding into gaseous diffusion, feeding into electromagnetic separation, each stage doing part of the work, the system as a whole could get there. It was an engineering solution born of pragmatism and urgency rather than elegance, and it consumed staggering resources. Oak Ridge, at its peak, employed over 75,000 people. Most of them had no idea what they were making. They knew their specific job: operate this valve, monitor this gauge, maintain this pump. But the larger purpose was secret. Workers joked that they were building nothing in enormous quantities. And while all of this was happening for uranium, the plutonium path was advancing on its own separate, equally massive track. Remember, Seaborg's team had shown that you could create plutonium-239 by bombarding U-238 with neutrons. Fermi's pile had proven that a chain reaction could produce those neutrons in quantity. So the idea was straightforward in concept. Build much larger reactors, run them at high power, breed plutonium inside uranium fuel, then chemically separate the plutonium from the uranium and fission products. Unlike isotope separation, this last step was chemical separation. Plutonium is a different element from uranium, so you can use chemistry to pull it out. That part, at least, was more tractable than the isotope nightmare. But building production reactors was its own enormous challenge. Fermi's pile in Chicago had operated at tiny power levels. The production reactors needed to run at hundreds of megawatts, millions of times more power, to produce plutonium in useful quantities. That meant solving the problem of heat removal, because all that fission energy had to go somewhere. It meant dealing with intense radiation fields. It meant understanding reactor physics at a level that was, in 1943, still largely theoretical. And it meant building everything at a brand new site in the desert of eastern Washington state, along the Columbia River, at a place called Hanford. Hanford is one of those stories that deserves its own space, because what happened there was engineering on a scale that borders on the surreal. The site was chosen for its remoteness, its access to the cold water of the Columbia River for reactor cooling, and the availability of hydroelectric power from Grand Coulee and Bonneville dams. The town of Hanford and several smaller communities were evacuated, families given a few weeks to leave land they'd farmed for generations. Within months, a workforce of over 50,000 people was building 3 massive production reactors, designated B, D, and F, along with chemical separation plants and hundreds of support buildings. It was an instant city in the sagebrush, and almost nobody there knew what they were building or why. The reactors themselves were graphite-moderated, water-cooled designs, conceptual descendants of Fermi's pile, but scaled up beyond anything Fermi had imagined. The B reactor, the first one completed, contained over 36,000 fuel tubes running horizontally through a graphite cube roughly 36 feet on each side. Aluminum-clad uranium fuel slugs, each one about the size of a roll of quarters, were loaded into the tubes by the hundreds of thousands. Cold water from the Columbia River was pumped through the tubes to carry away the heat. The irradiated water, now slightly radioactive, was held in retention basins to cool down before being released back into the river. An environmental practice that, decades later, would become one of the most significant contamination legacies of the nuclear age. But in 1944, that was a problem for the future. When the B reactor was first brought to full power in September 1944, something unexpected happened, something that nearly derailed the entire plutonium program, and that illustrates just how much the engineers and physicists were working at the edge of the unknown. The reactor started up fine. Power rose. Everything looked good. And then, after several hours, the power began to drop. Slowly at first, then faster. The reaction was dying. The operators were baffled. They checked for leaks, for control rod errors, for anything mechanical. Nothing. The reactor simply seemed to be poisoning itself. Within hours, it had shut down completely. And then, mysteriously, after about 11 hours, the power began to creep back up on its own. The reactor came back to life. It was Enrico Fermi and the physicist John Wheeler who figured out what was happening. And the explanation is one of those beautiful pieces of nuclear detective work that shows you just how strange the subatomic world really is. Here's what was going on. When uranium-235 atoms fission inside the reactor, they don't just split into 2 neat pieces and a couple of neutrons. They produce a whole zoo of fission products. Dozens of different radioactive isotopes, fragments of the original atom that are themselves unstable and begin decaying into other elements. One of the fission products is an isotope called tellurium-135. Now, tellurium-135 is radioactive, and it decays fairly quickly. Its half-life is only about 19 seconds. Into iodine-135. And iodine-135 is also radioactive, with a half-life of about 6.5 hours, and it decays into xenon-135. And xenon-135, this is the villain of the story, turns out to have one of the most extraordinary properties of any isotope ever discovered. It has an absolutely enormous appetite for neutrons. Its neutron absorption cross-section, which is just a measure of how likely it is to capture a passing neutron, is almost off the charts. It's roughly 2.5 million barns. A barn is the unit physicists use for this kind of thing, and most isotopes have cross-sections measured in single digits, or maybe tens of barns. Xenon-135 is in the millions. It's a neutron sponge like nothing else in nature. So what was happening in the B reactor was this. As the reactor ran, fission was producing tellurium, which decayed into iodine, which decayed into xenon-135. And the xenon was building up inside the fuel, quietly absorbing more and more of the neutrons that were supposed to be sustaining the chain reaction. It was like someone slowly closing a valve on the neutron supply. Eventually, so much xenon accumulated that it choked the reaction entirely. The reactor shut itself down. But here's the twist. Xenon 135 is itself radioactive, with a half-life of about 9 hours. So once the reactor stopped and fission ceased, no new xenon was being created, and the existing xenon began to decay away. After enough hours passed, the xenon levels dropped low enough that the chain reaction could sustain itself again, and the reactor crept back to life. It was a self-correcting problem, but only if you understood what was causing it. Now, this could have been a catastrophe for the schedule. If the reactor couldn't run at sustained power without periodically shutting itself down, the whole plutonium production timeline would collapse. But here's where a piece of quiet engineering foresight saved the entire program. When DuPont, the industrial contractor building the Hanford reactors, had been designing the B reactor, their engineers had insisted on adding extra fuel tubes beyond what the physicists said were necessary. The physicists had calculated that about 1,500 tubes would be sufficient. DuPont's engineers, being practical-minded people who had spent careers building chemical plants where things always went wrong in unexpected ways, pushed for more margin. They added enough tubes to bring the total to over 2,000. The physicists had grumbled about this. It seemed like wasted effort and material. But when the xenon poisoning problem appeared, those extra tubes turned out to be the solution. By loading additional uranium fuel into the spare tubes, the operators could boost the reactor's reactivity enough to overwhelm the xenon poisoning and push through it. The reactor could run at full power continuously. DuPont's conservatism, their instinct to overbuild, to leave margin for the unknown, saved the plutonium program. And it's a lesson that comes up again and again in engineering history. The people who build things for a living often understand something that the theorists sometimes miss, which is that the universe is full of surprises, and you'd better leave yourself some room. With the xenon problem solved, the Hanford reactors settled into production. Uranium fuel slugs went in one end, spent weeks being bombarded by neutrons inside the reactor, and came out the other end transformed, now containing small amounts of plutonium-239 mixed in with the remaining uranium and a stew of intensely radioactive fission products. Extracting that plutonium was its own nightmare. The irradiated fuel slugs were so radioactive that they had to be handled entirely by remote control, behind thick concrete walls, using periscopes and mechanical arms. The chemical separation process, developed largely at Oak Ridge on a pilot scale and then scaled up at Hanford, involved dissolving the fuel in acid and then using a series of chemical precipitation steps to isolate the plutonium from everything else. The workers who did this operated in vast concrete canyons, buildings 800 feet long called canyon buildings, where they could never directly see or touch what they were working with. Everything was done through remote manipulation. And at the end of this entire process, the plutonium emerged as a metal, silvery, warm to the touch from its own radioactivity, and extraordinarily dense. About 19.5 grams per cubic centimeter, denser even than gold. A sphere of plutonium the size of a baseball would weigh about 14 pounds. So by early 1945, the Manhattan Project had two paths to fissile material converging. Oak Ridge was producing enriched uranium-235, and Hanford was producing plutonium-239. But having the material was only half the problem. You also had to figure out how to assemble it into a bomb that would actually work. And this is where the story moves to the most secretive place of all, Los Alamos, New Mexico. Los Alamos was the brainchild of Robert Oppenheimer, who had been appointed scientific director of the weapons laboratory in 1942. Oppenheimer is one of those figures who seems almost too perfectly cast for his role. A tall, thin, chain-smoking theoretical physicist with piercing blue eyes, a gift for languages, an interest in Sanskrit poetry, and a charisma that could hold a room full of Nobel laureates spellbound. He was brilliant, complicated, and deeply aware of the moral weight of what he was building. General Groves chose him despite the fact that Oppenheimer had no administrative experience, no Nobel Prize, and a history of left-wing political associations that made the security people deeply uncomfortable. Groves saw something in him, a quality of intellectual leadership, an ability to synthesize across disciplines, a way of making the best physicists in the world want to follow him. And Groves was right. Oppenheimer turned out to be perhaps the most effective scientific leader of the 20th century, at least for those intense, compressed years on the Mesa. Los Alamos itself was built on a remote plateau in the Jemez Mountains at about 7,200 feet elevation, on the site of a former boys' ranch school. The location was chosen for its isolation. It was far from prying eyes, accessible only by a winding mountain road and surrounded by canyons and forest. Scientists and their families lived behind fences, their mail was censored, and their address was simply P.O. Box 1663, Santa Fe, New Mexico. Many of the world's most brilliant physicists, Fermi, Bohr, Bethe, Teller, Feynman, von Neumann, gathered in this unlikely place, living in hastily built housing, arguing about physics over meals in a communal dining hall, and working around the clock on problems that had never been attempted before. The fundamental challenge at Los Alamos was this: you have a quantity of fissile material, either uranium-235 or plutonium-239, and you need to bring it together into a supercritical mass fast enough that the chain reaction can build up and release an enormous amount of energy before the whole thing blows itself apart. That last part is crucial and easy to overlook. Think about what happens when a chain reaction starts in a bomb. The energy release is so rapid and so intense that it begins to heat and expand the material almost immediately. And as the material expands, it becomes less dense. The atoms move farther apart. Neutrons are more likely to escape without hitting another nucleus, and the reaction starts to fizzle. So there's a race between the chain reaction trying to multiply and release energy, and the material trying to fly apart and shut the reaction down. The bomb has to be designed so that the chain reaction wins that race, at least long enough to release a significant fraction of its potential energy. If the assembly is too slow, the bomb will produce a fizzle, a small explosion, maybe equivalent to a few tons of TNT, that scatters the material before most of it can fission. You'd waste almost all of your precious fissile material and produce a dud. And remember, each kilogram of this material had taken months and enormous industrial effort to produce. You could not afford a fizzle. For uranium-235, the bomb design turned out to be relatively straightforward, at least in concept. This was the gun-type design. Imagine a cannon barrel. At one end, you have a subcritical piece of uranium-235. At the other end, another subcritical piece. You fire one piece down the barrel into the other at high speed. When they slam together, the combined mass exceeds the critical threshold. A chain reaction ignites, and you get a nuclear explosion. The assembly speed didn't need to be extraordinarily fast because uranium-235 has a relatively low rate of spontaneous fission, meaning it doesn't produce many stray neutrons on its own that might trigger a premature chain reaction before the pieces are fully together. The physicists at Los Alamos were confident enough in this design that they never even tested it before using it in combat. The bomb dropped on Hiroshima on August 6, 1945, called Little Boy, was a gun-type uranium bomb, and it was the first and only time that design was used in war. It was also, remarkably, the first time it had ever been detonated. They were that sure it would work. But plutonium was a different story entirely, and this is where the real engineering genius of Los Alamos came into play. Early in the project, the plan had been to use the gun-type design for plutonium as well. But in the spring of 1944, a young physicist named Emilio Segre made a discovery that threw everything into chaos. Segre had been measuring the spontaneous fission rate of the plutonium coming out of the Hanford reactors, and he found that it was far higher than expected, about 5 times higher than the plutonium that had been produced in smaller quantities in cyclotrons. The reason was an isotope called plutonium-240, which was inevitably created alongside plutonium-239 in the reactor. Plutonium-240 has a very high spontaneous fission rate, meaning it's constantly spitting out stray neutrons, and in the reactor-produced plutonium from Hanford, there was enough plutonium-240 contamination that the material was essentially buzzing with neutrons all the time. This was devastating news for the gun-type design. The problem was speed. In a gun assembly, it takes roughly a millisecond, a thousandth of a second, to fire one piece of plutonium into the other. But with all those stray neutrons flying around from the plutonium-240, the odds were overwhelming that a neutron would trigger a premature chain reaction during that millisecond, before the pieces were fully together. You'd get a fizzle every time. The gun-type approach simply could not assemble plutonium fast enough. And you couldn't just remove the plutonium-240. It was chemically identical to plutonium-239, so chemical separation wouldn't work, and isotope separation of plutonium would have required building an entirely new industrial complex. There wasn't time, so the entire plutonium bomb program pivoted to an alternative approach that had been studied as a backup, a concept called implosion. And implosion is one of the most audacious engineering ideas anyone had ever attempted. Instead of slamming 2 pieces together in a gun barrel, you would take a sphere of plutonium and compress it, squeeze it inward from all directions, simultaneously using carefully shaped explosive charges. The compression would increase the density of the plutonium, bringing the atoms closer together, making neutron capture more likely, and driving the material past the critical threshold not by adding more material, but by making the existing material denser. It's a beautifully elegant idea in theory. In practice, it was an absolute nightmare. Think about what you're asking for here. You need an explosive wave, a detonation front, to converge perfectly inward on a sphere roughly the size of a grapefruit, arriving at every single point on that sphere's surface at exactly the same instant. Not roughly the same instant. Exactly. If one part of the wave arrives even a microsecond early, you don't get symmetric compression. You get a jet. The plutonium squirts sideways, like squeezing a wet bar of soap. Instead of a supercritical mass, you get a messy, asymmetric blob that fizzles or barely reacts at all. And the tolerances involved were unlike anything in the history of engineering up to that point. The detonation wave had to be spherically symmetric to within a few percent. We're talking about shaping an explosion, one of the most violent, chaotic physical events you can create, into something geometrically precise. Now, here's the thing about conventional explosives. When you detonate a block of high explosive, the detonation wave moves outward from the point of ignition. It's a diverging wave. What you need for implosion is a converging wave, one that moves inward. And you can't just wrap a ball of plutonium in a shell of explosive and set it off from one point, because then you'd get compression from one direction, not from all directions. So the question became, How do you take multiple detonation points on the outside of a sphere and shape all those outward-moving waves so they merge into a single, perfectly spherical, inward-moving wave? The answer came from a concept called explosive lenses, and the person who contributed perhaps the most crucial insight was a physicist named John von Neumann. Von Neumann was one of those figures who seemed to operate on a different intellectual plane from everyone else. He'd already made foundational contributions to mathematics, quantum mechanics, and game theory before the war. At Los Alamos, he brought his extraordinary mathematical mind to bear on the hydrodynamics of implosion, the physics of how shock waves move through materials. And his key realization was that you could use the same principle as an optical lens, but with explosives instead of glass. In an optical lens, light slows down when it enters glass, and by shaping the glass surface, you can bend and focus the light waves. Similarly, if you used two different types of explosive, one fast-burning, one slow-burning, and shaped the boundary between them just right, you could refract the detonation wave. You could bend it. You could take a detonation that starts at a point on the outer surface and reshape it into a flat wave, and then combine many of these flat waves around the sphere to create a converging spherical wave. It sounds almost elegant when you describe it that way, but the actual engineering was brutal. The explosive lenses had to be cast with extraordinary precision. Each one was a carefully shaped block containing two different explosive compositions, a fast outer explosive and a slow inner explosive, with the interface between them machined to exact mathematical curves. The whole assembly used 32 explosive lens segments fitted together like a three-dimensional puzzle, some shaped like pentagons and some like hexagons, arranged in the same geometric pattern as the panels on a soccer ball. Each lens had its own detonator, and all 32 detonators had to fire within a microsecond of each other. That required an electrical firing system of unprecedented precision. The person who led much of this explosive lens work was a physicist named George Kistiakowsky, a Russian-born chemist who was one of the world's leading experts on explosives and detonation. Kistiakowsky and his team spent months casting, testing, and refining these lens shapes. They'd set up test assemblies, detonate them, and use high-speed diagnostics to see whether the converging wave was truly spherical. Early results were discouraging. The waves were lumpy, asymmetric, full of jets and irregularities. Kistiakowsky's group iterated relentlessly, adjusting compositions, tweaking geometries, improving casting techniques. The explosive charges had to be free of voids, cracks, and density variations, because any imperfection would distort the wave. They were essentially trying to manufacture explosive components to the tolerances of precision machinery, using materials that were temperamental, dangerous, and nothing like metal or glass. And that was just the outer shell. Inside the explosive assembly sat the plutonium core itself, surrounded by a layer of natural uranium called a tamper. The tamper served multiple purposes. It reflected neutrons back into the core, which helped sustain the chain reaction, and its sheer inertia helped hold the assembly together for a few extra nanoseconds during the explosion, giving more of the plutonium time to fission before the whole thing blew apart. Those extra nanoseconds mattered enormously. In a nuclear detonation, the difference between a weapon that releases the energy equivalent of 1,000 tons of TNT and one that releases 20,000 tons can come down to how long the core stays together. And we're talking about differences measured in billionths of a second. There was another critical component nestled at the very center of the plutonium core, the initiator. This was a small device, about the size of a walnut, designed to release a burst of neutrons at precisely the right moment. the instant the plutonium reached maximum compression. You needed those neutrons to kickstart the chain reaction at the optimal moment. Too early, and the reaction begins before full compression, reducing yield. Too late, and the core might start to rebound before the chain reaction gets going. The initiator used in the Trinity device and the Nagasaki bomb was called an urchin, named for its resemblance to a sea urchin. And it worked by bringing together polonium-210 and beryllium. When the shock wave crushed the initiator, the polonium's alpha particles hit the beryllium atoms, which released neutrons through a nuclear reaction. It was a tiny, intricate mechanism buried at the heart of the most destructive device ever built, and its timing had to be perfect. So let's step back and appreciate the full picture of what this implosion device looked like. On the outside, a shell of precisely shaped explosive lenses, 32 segments, each with its own detonator, wired to a synchronized firing circuit. Inside that, a layer of fast explosive, then slow explosive, shaped to convert diverging detonation waves into a converging spherical wave. Inside that, the uranium tamper. Inside that, the plutonium core, about 6 kilograms of plutonium-239, machined into a sphere roughly the size of a tennis ball. And at the very center, the urchin initiator. The whole assembly was about 5 feet in diameter and weighed around 5,000 pounds. They called it the gadget, and nobody knew if it would work. That's the part that's easy to forget. By the spring of 1945, billions of dollars had been spent. In today's money, roughly 30 billion, and the entire plutonium path, which represented the majority of the weapons-grade material being produced, depended on an engineering concept that had never been tested. The uranium gun-type bomb was simple enough that the physicists were confident it would work without a test. They'd essentially fire it in combat without ever having detonated a prototype. But the implosion design was so complex, so dependent on everything working in perfect concert, that a test was absolutely necessary. If the lenses were slightly wrong, if the detonators were slightly out of sync, if the initiator fired at the wrong moment, any of these could mean failure. And failure didn't just mean a disappointing explosion. It could mean scattering plutonium across the desert without a nuclear yield, wasting irreplaceable material. So, they planned a test. They chose a site in the Jornada del Muerto desert in southern New Mexico. The Journey of the Dead Man, which is one of those names that history seems to have chosen with a dark sense of poetry. The test was codenamed Trinity, a name Oppenheimer selected, likely inspired by the poetry of John Donne. They built a 100-foot steel tower to hold the device, set up observation bunkers at 10,000 yards, and scattered instrument stations across the desert to measure blast pressure, radiation, and every other parameter they could think of. The test was scheduled for July 16, 1945. In the days leading up to it, the tension at Los Alamos was almost unbearable. Kistiakowsky was so confident in his explosive lenses that he reportedly bet Oppenheimer a month's salary against $10 that the device would work. Oppenheimer, ever the worrier, took the bet. Fermi, in his characteristically dry way, was taking side bets on whether the bomb would ignite the atmosphere, a possibility that had been studied and theoretically ruled out, but which still haunted some of the scientists. The weather was terrible. Rain and lightning swept through the test site in the early morning hours, and there were genuine fears that lightning could trigger the detonators prematurely. They delayed. They waited. The rain stopped. At 5:29 and 45 seconds on the morning of July 16, 1945, the firing circuit sent its signal. All 32 detonators fired within a microsecond. The explosive lenses shaped the detonation wave inward. The converging shock wave crushed the plutonium core from the size of a tennis ball down to roughly the size of a large marble, more than doubling its density. The urchin initiator released its burst of neutrons, and in the span of about a microsecond, a millionth of a second, roughly 80 generations of neutron multiplication occurred. Each fission event released energy and more neutrons, which caused more fissions, which released more energy and more neutrons, in an exponential cascade that released approximately 21 kilotons of energy, 21,000 tons of TNT equivalent, from about 6 kilograms of plutonium, of which only about 1 kilogram actually fissioned. The fireball was blinding. Observers 20 miles away felt the heat on their faces. The mushroom cloud rose to over 40,000 feet. The steel tower was completely vaporized, not melted, not knocked down, but turned into gas. The desert sand beneath the tower was fused into a glassy, mildly radioactive substance they later called trinitite, a greenish glass that you can still find fragments of today. The shockwave broke windows 100 miles away. Oppenheimer later said that the sight brought to mind a line from the Hindu scripture, the Bhagavad Gita. "Now I am become death, the destroyer of worlds." Kenneth Bainbridge, the physicist who directed the test, turned to Oppenheimer and said something more blunt. "Now we are all sons of bitches." And test director General Farrell described the experience as something no mere words could capture. The feeling that you were present at the moment the world changed irreversibly. And it had. Because now there were decisions to make, and they had to be made fast. The war in Europe was already over. Germany had surrendered in May. But the war with Japan continued, and an invasion of the Japanese home islands was being planned, an operation that military planners estimated could cost hundreds of thousands of American casualties and potentially millions of Japanese casualties. The question of whether to use this new weapon against Japan was not, in the summer of 1945, the agonizing moral debate it would later become in historical retrospect. For most of the military and political leadership, it was seen as a way to end the war quickly, without the catastrophic bloodshed of an invasion. There were dissenters, a group of scientists at the Chicago Metallurgical Laboratory, led by James Franck, had petitioned for a demonstration shot rather than a combat drop, hoping Japan could be convinced to surrender by witnessing the weapon's power without suffering its effects. Their petition, known as the Franck Report, was considered and ultimately set aside. On August 6, 1945, a B-29 bomber named the Enola Gay, piloted by Colonel Paul Tibbets, dropped Little Boy, the untested uranium gun-type bomb, on Hiroshima. The weapon detonated at an altitude of about 1,900 feet, with a yield of roughly 15 kilotons. The city was devastated. Estimates of the death toll vary, but approximately 70 to 80,000 people died immediately, with tens of thousands more dying in the weeks and months that followed from burns, radiation sickness, and injuries. 3 days later, on August 9th, a second B-29 called Boxcar dropped Fat Man, the plutonium implosion bomb, essentially a copy of the Trinity device, on Nagasaki. The yield was about 21 kilotons. Approximately 40,000 people died immediately, with a similar toll in the aftermath. Japan announced its surrender on August 15th. The world had entered the nuclear age, and almost immediately a new question began to take shape, one that would dominate global politics for the next half-century and beyond. If one nation could build these weapons, could others? And what would happen when they did? The answer came faster than almost anyone expected. And the story of how it happened is one of the most remarkable tales of espionage, scientific determination, and geopolitical pressure in modern history. So let's start with the Soviet Union, because that's where the first real shock came from. The Americans, in the summer of 1945, believed they had a comfortable lead, maybe a decade, maybe longer. General Groves himself estimated it would take the Soviets 15 to 20 years to build their own bomb. The reasoning seemed sound on the surface. The Manhattan Project had required an unprecedented industrial effort, billions of dollars, tens of thousands of workers, some of the greatest scientific minds on the planet, and access to raw materials that were difficult to obtain. Surely no other nation could replicate all of that quickly. And the Soviet Union, remember, had just fought the most devastating war in human history. Something like 27 million Soviet citizens died in World War II. Entire cities were rubble. Their industrial base in the western part of the country had been systematically destroyed. How could a nation in that condition possibly divert the resources needed to build a nuclear weapon? Here's the thing. They already had a head start, and the Americans didn't fully realize it. The Soviet nuclear program had been quietly underway since 1943, when physicist Igor Kurchatov was appointed to lead what the Soviets called Laboratory No. 2 in Moscow. Kurchatov was a brilliant physicist, charismatic, with a distinctive forked beard that became his trademark. He'd been working on nuclear physics before the war, and Soviet intelligence had been feeding him information about the Manhattan Project almost from the beginning. This is the espionage part of the story, and it's worth slowing down for. The most famous Soviet spy in the Manhattan Project was Klaus Fuchs, a German-born British physicist who had fled Nazi Germany as a young man, eventually became a British citizen, and was sent to Los Alamos as part of the British delegation working on the bomb. Fuchs was a committed communist. He'd joined the party in Germany before fleeing, and he believed that a nuclear monopoly held by any single nation was inherently dangerous, so he passed detailed information about the bomb's design to Soviet intelligence, and not just vague outlines. Fuchs had worked directly on the implosion design. He provided the Soviets with specifics about the explosive lens configuration, the dimensions of the plutonium core, the initiator design, the yields, essentially a blueprint for Fat Man. There were other spies too. Theodore Hall, a young physicist at Los Alamos, independently passed information to the Soviets. David Greenglass, a machinist at Los Alamos, provided sketches of the implosion lens molds to his brother-in-law Julius Rosenberg, who passed them along to Soviet handlers. Now, it's important to understand what this espionage did and didn't accomplish. It didn't hand the Soviets a bomb on a silver platter. You can't just read a set of plans and build a nuclear weapon. You still need enriched uranium or plutonium, which means you need reactors, you need separation plants, you need the entire industrial infrastructure. What the espionage did was save the Soviets enormous amounts of time. It told them which approaches worked and which didn't. It meant Kurchatov's team didn't have to explore dead ends that the Americans had already explored and abandoned. Think about how much time the Manhattan Project spent figuring out that gun-type assembly wouldn't work for plutonium. The Soviets already knew that. They knew implosion worked. They knew the geometry. They could focus their efforts. And focus they did. Stalin treated the nuclear program as an absolute top priority. He appointed Lavrenti Beria, the head of the secret police, one of the most feared men in the Soviet Union, to oversee the project. That tells you something about how seriously they took it. Beria was ruthless, terrifying, and extraordinarily effective at mobilizing resources. Under his direction, the Soviets built their own versions of the American facilities. They constructed a plutonium production reactor at a secret city called Chelyabinsk 40, later known as Chelyabinsk 65, in the Ural Mountains. They built gaseous diffusion plants for uranium enrichment. They recruited and conscripted thousands of workers, many of them prisoners from the Gulag system. The human cost was staggering and largely hidden from the world for decades. On August 29, 1949, just 4 years after Hiroshima, the Soviet Union detonated its first nuclear device, called First Lightning by the Soviets, or Joe 1 by the Americans, a somewhat dismissive nickname referencing Joseph Stalin. It was a plutonium implosion bomb, and its design was essentially a copy of Fat Man. The yield was about 22 kilotons. When American aircraft detected the radioactive fallout drifting across the Pacific, the intelligence community was stunned. 4 years, not 15, not 20, 4. And this changed everything. This single event, the Soviet bomb, is arguably the most consequential moment in the entire nuclear story after Hiroshima itself. Because now you had 2 nations with nuclear weapons, and neither one trusted the other, and both were rapidly building more. The arms race had begun in earnest. But here's where the story takes another turn, because fission bombs, the kind we've been talking about, the kind that destroyed Hiroshima and Nagasaki, those turned out to be just the beginning. Even before the war ended, physicists had realized there was something potentially far more powerful. And to understand it, you need to think about the opposite of fission. Instead of splitting heavy atoms apart, what if you could push light atoms together? What if you could fuse them? This is thermonuclear energy, fusion, and it's the process that powers the sun. Deep in the sun's core, where temperatures reach about 15 million degrees and the pressure is immense, hydrogen nuclei are squeezed together so hard that they overcome their natural electrical repulsion and merge, fusing into helium. When they do, a tiny bit of mass is converted into energy, our old friend E equals mc squared again, and the energy released per unit of fuel is actually much greater than fission. Fusion is, pound for pound, several times more energetic than splitting uranium or plutonium. The idea of a fusion weapon, a hydrogen bomb or H-bomb, had been floating around since the early days of the Manhattan Project. Edward Teller, a Hungarian-born physicist who'd come to the United States in the 1930s, had been almost obsessively interested in the concept. During the war, while everyone else at Los Alamos was focused on making fission weapons work, Teller kept pushing to work on what he called the super, a bomb that would use a fission explosion as a trigger to ignite a fusion reaction in a mass of hydrogen fuel. His colleagues found this frustrating. There was a war on. They had a specific job to do, and Teller kept wanting to skip ahead to the next, bigger thing. After the war, the debate over whether to build the hydrogen bomb became one of the most contentious scientific and political arguments of the 20th century. Oppenheimer, who had led Los Alamos, was against it. He and the General Advisory Committee of the Atomic Energy Commission recommended against a crash program to develop the super, arguing that it was unnecessary, potentially genocidal in scale, and that pursuing it would only accelerate the arms race. Teller was furious. He lobbied politicians. He argued passionately. He felt that the Soviet threat demanded the most powerful deterrent possible. The debate split the physics community. Former colleagues stopped speaking to each other. It was bitter and personal in ways that still echo today. President Truman settled the question in January 1950, ordering a crash program to develop the hydrogen bomb. And here's where the engineering gets fascinating again, because the original concept, Teller's classical super, turned out not to work. The idea was relatively straightforward in concept. Detonate a fission bomb next to a container of liquid deuterium, which is a heavy form of hydrogen, and hope the heat from the fission explosion would be enough to ignite a self-sustaining fusion reaction that would propagate through the fuel. But when mathematicians ran the calculations, and this is where some of the earliest computer calculations in history come in, done on the ENIAC and other early machines, they found that the fusion reaction kept fizzling out. The heat dissipated too quickly. You couldn't get the deuterium to sustain a burn. The breakthrough came from an unlikely collaboration. In 1951, Stanislaw Ulam, a Polish-born mathematician at Los Alamos, had a key insight. Instead of relying on the direct heat of the fission explosion to ignite the fusion fuel, what if you used the radiation, the X-rays, produced by the fission primary to compress the fusion fuel first? Compression would dramatically increase the density and temperature of the fuel before ignition, making a sustained fusion reaction possible. Teller seized on this idea, refined it, and the result was what's now called the Teller-Ulam design. And this is the architecture that makes modern thermonuclear weapons possible. Let me walk you through how it works, because it's genuinely one of the most extraordinary pieces of engineering ever conceived, even if its purpose is terrifying. Picture a weapon with two stages inside a single casing. The first stage is a fission bomb, a plutonium implosion device, like Fat Man, but refined and more efficient. This is called the primary. The second stage, called the secondary, is a cylinder containing fusion fuel, typically lithium deuteride, a solid compound that's much easier to handle than liquid deuterium. Inside the secondary, running down its center like a candle wick, is a rod of plutonium called the spark plug. Here's what happens when you detonate it. The primary fires first. The implosion device goes off, producing an enormous burst of energy. Now, about 80% of that energy comes out as X-rays, not as a physical blast wave. These X-rays fill the interior of the weapon's casing, which is lined with a material, usually uranium, that reflects and channels them. The X-rays create what physicists call a radiation channel, and they travel at the speed of light, reaching the secondary almost instantaneously. When these X-rays hit the outer surface of the secondary, they heat it so intensely that the surface material ablates. It explodes outward. And by Newton's third law, that outward explosion of the surface creates an equal and opposite inward force, compressing the fusion fuel to extraordinary density. At the same time, the plutonium spark plug at the center of the secondary is also compressed by this implosion, and it goes critical. It starts fissioning, heating the fusion fuel from the inside. So you have compression from the outside and heating from the inside simultaneously, and the fusion fuel ignites. The result is a weapon with essentially no upper limit on yield. You can add more stages. You can make the secondary larger. The first American thermonuclear test, codenamed Ivy Mike, took place on November 1, 1952, at Eniwetok Atoll in the Pacific. It used liquid deuterium as fuel, which required an enormous refrigeration plant. The device weighed about 82 tons and was essentially a building, not a deliverable weapon. But the yield was staggering. 10.4 megatons. That's 10,400 kilotons. Roughly 700 times the power of the Hiroshima bomb. It vaporized the island of Alugalab entirely. The island simply ceased to exist, replaced by an underwater crater more than a mile wide. The Soviets weren't far behind. Their first true thermonuclear test, in November 1955, demonstrated a deliverable weapon, one that could actually be dropped from an aircraft. And then the race escalated to almost incomprehensible scales. on October 30th, 1961. The Soviet Union detonated the largest nuclear weapon ever tested. It was called Tsar Bomba, the king of bombs, and it was dropped from a specially modified Tu-95 bomber over the Novaya Zemlya archipelago in the Arctic. The yield was approximately 50 megatons, 50 million tons of TNT equivalent. The fireball was 5 miles in diameter. The mushroom cloud rose to over 40 miles high into the mesosphere. The shockwave circled the Earth 3 times. Windows were broken in Finland and Norway, hundreds of miles away. The flash was visible 600 miles from the detonation point. And here's the thing that really puts it in perspective. The bomb was actually designed for 100 megatons. They deliberately scaled it back by replacing the uranium tamper in the 3rd stage with lead, which reduced the yield by half, but also dramatically reduced the fallout. Even the Soviets thought 100 megatons was too much. Andrei Sakharov, the physicist who was instrumental in designing Soviet thermonuclear weapons, later became one of the most prominent advocates for nuclear disarmament. The experience of creating these weapons changed him profoundly. He saw what he had built, understood what it meant, and spent the rest of his life trying to put the genie back in the bottle. He won the Nobel Peace Prize in 1975 for his efforts, though the Soviet government wouldn't let him travel to accept it. By the early 1960s, both superpowers had arsenals numbering in the thousands of warheads, mounted on intercontinental ballistic missiles that could cross the ocean in 30 minutes, carried by submarines lurking silently beneath the waves, loaded into the bomb bays of strategic bombers on constant alert. This was the architecture of deterrence. The idea that neither side would dare launch a first strike because the other side would always retain enough surviving weapons to retaliate with devastating force. The doctrine had a grimly appropriate name: Mutual Assured Destruction, or MAD. And it worked, in the sense that no nuclear weapon has been used in conflict since Nagasaki. But the margin of safety was thinner than most people realize, and the stories of how close the world came to accidental or unauthorized nuclear war are enough to keep you awake at night, which is maybe not ideal given what we're going for here, but these stories matter too much to skip. Let's start with one that happened right in the middle of the Cuban Missile Crisis, October 1962, when the world was already balanced on a knife's edge. A Soviet submarine, B-59, was lurking in the Caribbean, and American destroyers had found it. They started dropping practice depth charges, small explosive charges meant to force the submarine to surface and identify itself. Now here's what the Americans didn't know. B-59 was carrying a nuclear torpedo, a single torpedo with a warhead roughly comparable to the Hiroshima bomb, and the crew had been out of radio contact with Moscow for days. They didn't know whether war had already started on the surface. The depth charges were shaking the hull. The air conditioning had failed. Temperatures inside the submarine had climbed past 100 degrees Fahrenheit. Carbon dioxide levels were rising, and crew members were fainting at their stations. The captain, Valentin Savitsky, reportedly became convinced that World War III had begun. He ordered the nuclear torpedo to be assembled and prepared for firing. And here's where the story turns on one person. On most Soviet submarines, launching a nuclear weapon required the agreement of 2 officers, the captain and the political officer. Both of them were ready to fire. But B-59 happened to be the flotilla flagship, which meant there was a 3rd officer aboard, the flotilla commander, a man named Vasily Arkhipov, and all 3 had to agree. Arkhipov refused. He argued that they should surface and await orders from Moscow instead. There are accounts that say the argument was intense, that voices were raised, that Savitsky was furious. But Arkhipov held firm. The submarine surfaced, the situation de-escalated, and a nuclear torpedo was not fired at the American fleet in the Caribbean in October of 1962. Think about what that means. One man, in a sweltering submarine, overruling his captain during what he had every reason to believe was an active war, may have prevented a nuclear exchange between the United States and the Soviet Union. If B-59 had been any other submarine in the flotilla, one without a flotilla commander aboard, the launch protocol would have required only 2 approvals, and both of those officers were ready to go. The fate of civilization, in that moment, hinged on a bureaucratic quirk of naval organization. Arkhipov didn't receive widespread recognition during his lifetime. He died in 1998. It wasn't until years later that historians and journalists pieced together the full story of what happened aboard B-59, and he's now sometimes called the man who saved the world. Whether that's an exaggeration or not, the underlying point is hard to argue with. The system came very, very close to failing, and that wasn't the only close call during the Cuban Missile Crisis. On October 27, 1962, the same day B-59 was being depth-charged, a U-2 spy plane on a routine air sampling mission near the North Pole accidentally strayed into Soviet airspace over Chukotka. Soviet MiGs scrambled to intercept it. American F-102 fighters were sent from Alaska to escort the U-2 back, and those F-102s were armed with nuclear-tipped air-to-air missiles. Nuclear air-to-air missiles. That was a real thing in the early 1960s. The Genie rocket, designed to take out formations of enemy bombers with a small nuclear blast. The authorization to use those missiles rested with the individual pilots. If the Soviet MiGs had engaged the American fighters, a pilot could have made the decision to fire a nuclear weapon on his own authority, over Soviet territory, during the most tense moment of the Cold War. It didn't happen, but the fact that the scenario was even possible tells you something about how the systems of control were designed, or rather, how they weren't fully designed yet. So let's talk about that for a second, because this is a thread that runs through the entire nuclear age. The tension between keeping weapons ready to use instantly and making sure they can't be used by mistake or without proper authorization. These are fundamentally opposing requirements. If you build in too many safeguards, you risk a scenario where you can't retaliate fast enough after a surprise attack, and your deterrent loses credibility. If you build in too few, you risk accidental or unauthorized launch. And the history of nuclear weapons is full of moments where that balance tilted dangerously. In the 1950s and early 1960s, the security mechanisms on American nuclear weapons were surprisingly rudimentary. Strategic bombers sat on runways loaded with live nuclear weapons, ready to take off on minutes' notice. The physical safeguards on the bombs themselves were minimal. There was a real concern within the government, particularly from Robert McNamara when he became Secretary of Defense in 1961, that a rogue pilot, a mentally unstable officer, or a miscommunication could lead to an unauthorized nuclear detonation. McNamara pushed hard for the installation of permissive action links, or PALs, on American nuclear weapons. These were essentially coded locking devices, electromechanical systems that required a specific code to be entered before the weapon could be armed. Without the correct code, the weapon was inert. Think of it like a combination lock on the most dangerous object ever created. But here's the kicker. The military resisted PALs for years. The Strategic Air Command, under General Curtis LeMay and his successors, worried that PALs would introduce delays or failure points that could prevent retaliation after a Soviet first strike. And when PALs were finally installed on Minuteman ICBMs, the land-based missiles sitting in silos across the American Midwest, there's a well-documented claim, confirmed by multiple former launch officers, that the Air Force set the PAL codes to all zeros. 8 zeros. 000000000 for roughly 15 years. The codes were essentially bypassed because the operational commanders prioritized launch readiness over launch security. The system that was supposed to prevent unauthorized use was quietly rendered meaningless by the people responsible for maintaining it. Now, there's some debate about the exact details and timeline of the all zeros story, and some former officials have pushed back on the specifics. But the broader point is well established. There was a persistent institutional tension between civilian authorities who wanted tighter controls and military commanders who wanted maximum readiness, and that tension sometimes produced outcomes that would alarm anyone who thought about them carefully. And then there are the accidents. The United States military uses the term broken arrow for incidents involving nuclear weapons, accidents that don't create a risk of war, but do involve damage to, loss of, or accidental detonation of a nuclear weapon's conventional explosives. And there have been dozens of them. In January 1961, a B-52 bomber broke apart in midair over Goldsboro, North Carolina, and dropped 2 Mark 39 hydrogen bombs. Each one had a yield of about 3 to 4 megatons, hundreds of times more powerful than Hiroshima. One of the bombs went through its arming sequence as it fell. It had a series of safety mechanisms, and all but one of them failed or were bypassed during the fall. A single low-voltage switch, one simple electrical component, was the only thing that prevented a full thermonuclear detonation over rural North Carolina. A government document declassified in 2013 confirmed this. One switch. Parker F. Jones, a nuclear weapons safety engineer at Sandia National Laboratories, wrote in a 1969 report that one simple dynamo technology, low-voltage switch, stood between the United States and a major catastrophe. The other bomb buried itself so deep in muddy farmland that it was never fully recovered. Parts of it are still there, in the ground, in North Carolina, to this day. In 1966, a B-52 collided with a refueling tanker over Palomares, Spain, and dropped 4 hydrogen bombs. The conventional explosives in 2 of them detonated on impact, scattering plutonium across Spanish farmland. A third landed intact. The fourth fell into the Mediterranean Sea and wasn't recovered for nearly 3 months. The cleanup involved removing over 1,400 tons of contaminated soil and shipping it back to the United States. Spanish tomato farmers watched American soldiers in protective suits digging up their fields. The diplomatic fallout was enormous. These are just the incidents we know about in detail. The Soviet Union had its own broken arrows, many of which remain classified or poorly documented to this day. Submarines were lost, weapons were damaged, reactors failed. The nuclear-powered submarine K-19, which the Soviets rushed into service in 1961, suffered a reactor coolant leak that exposed the crew to lethal doses of radiation. The crew improvised repairs to prevent a full meltdown, and several of them died from radiation exposure within weeks. It wasn't a weapons accident exactly, but it illustrates the broader pattern. These systems were enormously complex, operated under extreme conditions, by human beings who were tired, stressed, and sometimes working with inadequate equipment. But perhaps the most harrowing category of close calls involves false alarms, moments when one side's early warning systems indicated that a nuclear attack was underway, and the people monitoring those systems had to decide in minutes whether to report an incoming strike that could trigger retaliation. On September 26, 1983, a Soviet lieutenant colonel named Stanislav Petrov was the duty officer at Serpukhov 15, the command center that monitored the Soviet Union's satellite-based early warning system. Shortly after midnight, the system reported that an American Minuteman, ICBM, had been launched toward the Soviet Union. Then it reported a second launch, then a third, then a fourth and a fifth. 5 missiles incoming. Petrov's job was straightforward on paper. If the system detected a launch, he was supposed to report it up the chain of command, which would likely trigger a retaliatory strike. But something felt wrong to him. 5 missiles didn't make sense as a first strike. The Americans had thousands of warheads, and a real attack would involve hundreds or thousands of missiles, not 5. The system was also relatively new and hadn't been fully proven. Petrov made a judgment call. He reported the alert as a system malfunction rather than a genuine attack. He was right. The satellite system had been fooled by sunlight reflecting off high-altitude clouds over the American Midwest, creating infrared signatures that looked like missile launches. If Petrov had followed protocol and reported the launches as real, the Soviet leadership, already on edge because of the recent shoot-down of Korean Airlines, Flight 007, and a major NATO exercise called Able Archer, might well have launched a retaliatory strike against the United States. Petrov wasn't rewarded for his decision. He was initially praised, then quietly reassigned. The incident was kept secret for years. He later said he wasn't sure he'd done the right thing. Not because he doubted his judgment about the false alarm, but because he had violated his orders, and he understood that the entire system of deterrence depended on people following their orders. If everyone along the chain started making personal judgment calls, the system's credibility would collapse. It's a paradox that sits at the heart of nuclear deterrence. The system works only if everyone believes retaliation is automatic and certain, but making it truly automatic and certain means removing the human judgment that might prevent a catastrophic mistake. And this brings us to something that became increasingly important as the arsenals grew and the delivery systems got faster: arms control. Because by the mid-1960s, both sides were beginning to recognize that the arms race itself was becoming a source of danger, independent of any political conflict. More weapons meant more accidents, more false alarms, more chances for something to go wrong. And the weapons were getting harder to defend against, which meant both sides kept building more of them in an endless spiral. The first major breakthrough came in the late 1960s, and it wasn't really about reducing weapons. Not yet. It was about something more fundamental. It was about talking. See, for most of the first 2 decades of the nuclear age, the United States and the Soviet Union were building arsenals largely in the dark, each side guessing at what the other had, each side imagining the worst. And when you imagine the worst, you build more. You build extra, just in case. That's the spiral. But by the mid-1960s, a few things had changed. Reconnaissance satellites, Corona for the Americans, Zenit for the Soviets, were giving each side a much clearer picture of what the other actually had, and what they could see was sobering. Not because the other side had more than expected, necessarily, but because the sheer scale of what both sides had built was becoming absurd by any rational measure. The United States had over 30,000 nuclear weapons by the mid-1960s. The Soviet Union was catching up fast, and a new technology was threatening to make everything worse: anti-ballistic missiles, or ABMs. Here's why ABMs were so destabilizing, and this is a little counterintuitive. You'd think that a defensive system, something that shoots down incoming missiles, would make things safer. But in the logic of nuclear deterrence, it does the opposite. If one side builds a missile defense system that actually works, the other side's deterrent becomes unreliable. If your missiles might get shot down before they reach their targets, then your ability to retaliate is in question. And if your retaliation is in question, the other side might start to think they could launch a first strike and survive. So what do? You build more missiles, enough to overwhelm the defense, and then the other side builds more defenses, and then you build more missiles. It's an endless, ruinously expensive escalation, and both sides could see it coming. So in 1969, the United States and the Soviet Union began the Strategic Arms Limitation Talks, SALT as they came to be known. And in 1972, they produced two landmark agreements. The first was the Anti-Ballistic Missile Treaty, which essentially said, neither side will build a nationwide missile defense system. Each side was allowed just 2 ABM sites, later reduced to 1. That's it. And the reasoning was exactly what I just described. By agreeing not to defend, both sides preserved the other's ability to retaliate, which preserved deterrence, which preserved stability. It sounds insane when you say it out loud. We're going to keep ourselves safe by agreeing to remain vulnerable. But that was the logic. And honestly, it worked for decades. The second agreement was SALT I itself, an interim agreement that froze the number of strategic ballistic missile launchers on both sides at existing levels. It didn't reduce anything. It just said, okay, we'll stop building more of these particular delivery systems. It was a modest step, but it was the first time the two superpowers had ever agreed to any limit on their strategic arsenals, and the fact that they could sit across a table and negotiate about these weapons at all, that was the real breakthrough. It established a framework, a language, a set of expectations. It said, we are adversaries, but we share an interest in not destroying the world. Now, SALT I had enormous loopholes. It limited launchers, but not warheads. And by this time, both sides were developing MIRVs, multiple independently targetable re-entry vehicles. Remember, a single missile could carry several warheads, each aimed at a different target. So you could technically obey the launcher limits while dramatically increasing your actual number of deliverable warheads. And that's exactly what happened. Through the 1970s, both sides MIRVed their missiles aggressively. The total number of deployed warheads kept climbing, even as the number of launchers stayed roughly flat. By the late 1970s, the combined arsenals peaked at something like 70,000 nuclear weapons. 70,000. That's enough to destroy every major city on Earth many times over, with plenty left for military targets, infrastructure, and everything else. SALT II was signed in 1979 by Jimmy Carter and Leonid Brezhnev. It tried to address some of these gaps, setting limits on the total number of delivery vehicles, including bombers, and putting some constraints on MIRVed missiles. But SALT II was never ratified by the U.S. Senate. The Soviet invasion of Afghanistan in December 1979 killed whatever political will existed for ratification. Both sides more or less observed its limits anyway, informally, but the failure of SALT II was a real setback. It showed how fragile arms control was, how dependent it was on the broader political relationship. And then the 1980s happened. Ronald Reagan came into office in 1981 with a very different posture toward the Soviet Union. His administration undertook a massive military buildup, including new missile systems like the MX Peacekeeper and the deployment of Pershing 2 intermediate-range missiles in Europe. And in 1983, Reagan announced the Strategic Defense Initiative, SDI, quickly nicknamed Star Wars, a research program aimed at building a space-based missile defense system that could theoretically shoot down Soviet ICBMs in flight. Now, whether SDI could ever actually work was debatable. Most physicists were deeply skeptical, but the Soviets took it seriously. From their perspective, it threatened to undermine the entire logic of the ABM Treaty. If the Americans could defend against a retaliatory strike, then deterrence was broken. This was one of the tensest periods of the Cold War. The Soviets were genuinely frightened, more frightened than many Americans realized at the time. The Able Archer exercise in November 1983, the same one that formed part of the backdrop to Petrov's false alarm, actually caused elements of the Soviet military to begin preparing for a possible American first strike. We came closer to nuclear war in 1983 than most people know. But here's where the story takes a turn that nobody predicted. In March 1985, a relatively young, relatively unknown figure named Mikhail Gorbachev became General Secretary of the Communist Party of the Soviet Union. And Gorbachev was different. He had grown up in the Soviet system, risen through its ranks, but he could see that the system was failing, economically, socially, morally. The arms race was consuming resources the Soviet Union couldn't afford, and Gorbachev was genuinely, personally horrified by nuclear weapons. He later said that Chernobyl in 1986, the catastrophic nuclear reactor accident in Ukraine, crystallized his thinking. If a single reactor could contaminate vast stretches of Europe, what would a nuclear war do? Gorbachev and Reagan met at Reykjavik, Iceland, in October 1986, and what happened there was extraordinary. The two leaders, sitting across from each other, began proposing deeper and deeper cuts. At one point, they were seriously discussing the elimination of all nuclear weapons. All of them. The conversation ultimately broke down over SDI. Gorbachev wanted Reagan to confine the program to the laboratory. Reagan refused. But the fact that two Cold War leaders had come that close to agreeing on total nuclear disarmament was remarkable. It showed that the unthinkable was, at least for a moment, thinkable. What did come out of this period was the Intermediate Range Nuclear Forces Treaty, the INF Treaty, signed in 1987. This was genuinely historic. It didn't just limit a category of weapons, it eliminated an entire class of them. All ground-launched ballistic and cruise missiles with ranges between 500 and 5,500 kilometers, gone. Both sides destroyed nearly 2,700 missiles. It was the first treaty that actually reduced nuclear arsenals, rather than just capping them. And it included something that would have been unimaginable a decade earlier: on-site inspections, American inspectors in Soviet facilities, Soviet inspectors in American facilities, verification, trust, but verify, as Reagan liked to say. Then the Berlin Wall fell in 1989. The Soviet Union dissolved in 1991. And suddenly, the entire framework of nuclear deterrence, two superpowers, locked in ideological struggle, each holding the other at bay with the threat of annihilation. That framework just evaporated. The Cold War was over. What followed was a period of remarkable nuclear arms reduction. The Strategic Arms Reduction Treaty, START I, signed in 1991, required both sides to reduce their deployed strategic warheads to 6,000 each, with corresponding limits on delivery systems. START II, signed in 1993, went further, banning mirved ICBMs entirely, though it never fully entered into force. The Moscow Treaty of 2002 and New START in 2010 continued the reductions. From that peak of roughly 70,000 combined warheads, the global stockpile has come down to around 12 or 13,000 today. That's still an almost incomprehensible amount of destructive power, but it's a fraction of what it was, And yet, the story doesn't end with a neat resolution, does it? Because here we are, and nuclear weapons haven't gone away. 9 countries now possess them: the United States, Russia, the United Kingdom, France, China, India, Pakistan, Israel, and North Korea. The INF Treaty collapsed in 2019, with the United States withdrawing after accusing Russia of violations. New START was extended, but its future is uncertain. China is expanding its arsenal significantly. North Korea has conducted 6 nuclear tests and continues developing missiles that could reach the continental United States. Pakistan and India, 2 countries that have fought multiple wars against each other, sit across a border with nuclear weapons on hair-trigger alert. The risk of nuclear terrorism, a non-state actor acquiring enough fissile material to build even a crude device, remains a concern that keeps intelligence agencies up at night. And the weapons themselves have continued to evolve. Modern warheads are smaller, more accurate, and more reliable than anything from the Cold War era. The United States is in the middle of a $1 trillion modernization program, upgrading all 3 legs of its nuclear triad: new Columbia-class ballistic missile submarines to replace the aging Ohio-class, the new B-21 Raider stealth bomber, and the Sentinel YCBM to replace the Minuteman III, which has been in service since the 1970s. Russia has developed new systems specifically designed to evade missile defenses: hypersonic glide vehicles like the Avangard, which rides atop an ICBM and then glides through the atmosphere at Mach 20 or more, maneuvering unpredictably to defeat interceptors. There's the Poseidon, an autonomous nuclear-powered torpedo designed to cross entire ocean basins and detonate near coastal cities, generating a radioactive tsunami. Whether all of these systems work as advertised is an open question, but their existence tells you something about where things are heading. So, where does that leave us? You know, I've been talking for a while now, walking through this whole story from the ancient Greeks, wondering whether you could keep cutting matter in half forever. Through Rutherford and Bohr, figuring out the structure of the atom. Through that frantic wartime race to build the bomb. Through the moral anguish of the scientists who built it. Through the Cold War's terrifying logic of mutually assured destruction. Through the close calls that almost ended everything. Through the painstaking work of arms control that pulled us back from the brink. And I think the thing that strikes me most, after all of it, is how much of this story comes down to individual human beings making decisions under impossible pressure. Oppenheimer choosing to lead the project, then spending the rest of his life haunted by what he'd built. Truman deciding to use the bomb on a living city. Vasily Arkhipov saying no in a submarine where 2 other officers said yes. Stanislav Petrov trusting his gut over his instruments. Andrei Sakharov, the father of the Soviet hydrogen bomb, becoming the Soviet Union's most famous dissident because he couldn't live with what he'd helped create. These weren't abstract forces of history. These were people. Tired, scared, brilliant, flawed people. And the world we live in today exists because of the specific choices they made in specific moments. The physics of nuclear weapons is elegant and terrifying. The engineering is ingenious. But the human story, the politics, the fear, the miscalculation, the occasional act of extraordinary courage, that's what actually determines whether these weapons get used. And so far, since Nagasaki, on August 9th, 1945, they haven't been. That's almost 80 years. It's the longest stretch of great power peace in modern history. And how much of that is because of nuclear deterrence, and how much is despite it? Well, that's a question historians and strategists will argue about for as long as they're are historians and strategists. What I do know is this: the knowledge can't be uninvented. The physics is out there, in textbooks, in the fundamental structure of the universe. You can't put it back. So the challenge, the permanent, ongoing, never-finished challenge, is managing it, building systems and treaties and norms and relationships that keep these weapons from ever being used again. It's imperfect work. It depends on fallible people and fragile institutions, but it's the most important work there is. And maybe that's a strange thing to think about as you're lying there, drifting off. But there's something oddly comforting in it too, in knowing that throughout this whole long, frightening story, again and again, when it mattered most, someone chose correctly. Someone said no, or someone picked up the phone, or someone sat down at a table with an adversary and found a way to step back from the edge. The story of nuclear weapons is terrifying, yes, but it's also, in its strange way, a story about the stubborn persistence of human reason, even in the most unreasonable circumstances. So let that thought settle. The world is still here. You're still here, warm and safe, and the night is quiet. And all those complicated, beautiful, frightening ideas about atoms and energy and chain reactions and deterrence, they can rest now too. They'll still be there in the morning if you want them. But for now, just let them go. Let them dissolve like neutrons scattering into the dark, and let yourself drift into sleep.